first, I kind of started this by pulling just the explanation from your textbook because it's good to kind of learn how to read math a little bit. So to motivate the precise definition of a limit, let's consider this function. So this is a piecewise function, 2x minus 1. What would 2x minus 1 look like?
Line.
It's a line.
This way.
Y-intercept is
-1.
-1. Slope is
2/1.
2 over 1. Okay, and we're on this line everywhere except when?
3. When x equals 3.
Okay, so essentially, like if you were to graph it, that is an open circle right there. And my second piece, it's 6 when x equals 3. That's just another dot. Okay, so that's my piecewise. I have a line with a hole in the middle and just another point. Okay, so would you guys agree that the limit as I approach 3 is equal to 5?
Yeah.
If you're approaching 3, you're on this line. Limit laws say we could just plug in the 3 and we get out 5. Because the limit doesn't care what happens at the point just as we approach it, right? Okay, if I want to be more specific about what's going on with my y values, because I know as I'm approaching 3, are my y's equal to 5? No, they're getting closer to 5, but not actually equal to that. So, my question is, how close to 3 would x have to be so that f of x, where y differs from 5 by less than 1/10? Okay, so if I want to be within a 1/10 of accuracy, that means I need something between 4.9 and 5.1. How close would x have to be to 3? Because we know it's not, we don't have to put in 3 exactly. But you know when we made those tables, right? The closer we got to a certain value, then the closer the y got to 0.1. So this is kind of like our motivation here. If you are trying to measure distance between two things, distance is always positive, so it's an absolute value. Okay, so I could measure the distance from a point x to a point 3 by doing the absolute value. For my y's, I could do the absolute value of f of x minus 5. So our problem is to find a number delta. Okay, so this is a delta. Such that this says the distance between f of x and 5. So the distance between the y value of my graph and 5 is less than 1/10 if the distance between x minus 3, between x and 3, is less than delta. So we're basically figuring out, okay, how close do we have to be? Whatever that magic number is, that's my delta. So if my x is within delta, my y would be in the range of values I wanted. Okay? Your textbook uses this a lot, the absolute value of x minus 3 is between 0 and delta, but I don't really do that. It's kind of redundant. We already know the absolute value is positive. So just know if you're looking at your book, they write that as a compound inequality, and that's just really not necessary. We know it's greater than 0. We know absolute value is positive. Okay, so I am doing a little magic here, and I'm just telling you what this number is. Later we're going to figure out how we find it. But let's say if the distance between x and 3 was 500. Okay, then the distance between f of x, that was my y, right? The equation of y, we were on that line, that was 2x minus 1. So I could change that to 2x minus 1. 2x minus 1 minus 5 will give me 2x minus 6. Do you agree with that?
Yeah.
Since 2 is positive, can I factor a 2 out of the absolute value?
Yeah.
So that's 2 times the absolute value of x minus 3. Okay. But I gave you this magical, you don't know where I got it yet, but I said the absolute value of x minus 3 was less than delta. So this would have to be less than 2 times my delta, my 0.05, which is 1/10. So this is kind of like a proof. I just proved that if we are within 5/100ths of 3, so if I pick an x between 2.95 and 3.05, my y value will be within 1/10 of 5.
What math level class did we do proofing at? Was that in trade?
Yeah, you probably did some in geometry. Okay, yeah, we did proofs in trig.
Okay.
So, essentially what it's saying is then, if x is between 2.95 and 3.05, then y will be between 4.9 and 5.1. Okay, that's what we just found. Kind of. I'm using that term found loosely because I just kind of gave you the x that worked.
Kind of like stats.
No, it just has some weird variables.
Where did we get
I was just saying.
the 2.95 and is that?
That's because I told you up here, let's say we take the distance between x and 3 to be less than 500.
Oh, so it's
So
plus
if
or
it's 3 minus 500, 3 plus 500. Yes. So, we basically just found a formula. So if you want to be within 1/10 of the true answer, I'm telling you, you need to use x's that are within 5/100ths of the correct answer. Okay, but if it's a true limit, we should be able to get as accurate as possible. So you might want to come back at me and say, okay, what if I want to be within 100? I want to be more accurate. I want to be within 100. I should then be able to tell you what window of x's should be possible. So that is what we're doing when we talk about an epsilon delta proof. So the actual definition here. So the limit as x approaches a of a function is equal to L if for every number, this is an epsilon, greater than 0, so it's a positive number, there is a delta greater than 0, such that if the distance between x and a is less than delta, and the distance between f of x and L is less than epsilon.
Is there going to be an in bracket?
I mean, I was just kind of saying, this is like the true definition of a limit. So if you're reading a calc book, this is what it means to have a limit. So it's telling you, you can increase your accuracy in your y's just by basically taking a smaller window of x values. So I want to kind of talk about what this means a little bit, because this is super confusing. Another way of thinking about it, okay? Here's my x, all right? Here's my window for x. So A is kind of like my target. That's my number I'm approaching. So we're trying to find a window of values. What range of values should I pick so that when I find my y, it falls within the correct window on my limit? Usually, we're going to have this definition on our limits. We'll know how accurate we need to be, and we'll have to adjust the window on our x's to get there. In terms of a graph, okay, here's my a. So remember, we're doing the limit as x approaches a of a function is equal to L. So would you guys agree? If we're on this function, my limit is approaching L as x approaches a. So if you have some range of values, some epsilon, you want to be within 1/2. Okay, so of the true answer. So that'd be the true answer. Plus and minus 1/2. So basically anything in this blue window is acceptable. So if I want to be in that blue window, I would have to pick something in this range. Would you guys agree? So if we track that down, that's telling me my A's have to fall within this window. I have another graph I pulled up just to kind of illustrate this a little more and try to make sense of it. Okay, so if I look at this one, here is my limit. Okay, so 1 is the actual x I'm approaching, 3 is the limit. So if you want to look at this, if I want to be within a half, if 3 is the actual answer, then I would need something in between 2.5 and 3.5. Agreed? In order to get that, I'm going to have to pick an x that falls in this window. So my x's will have to be between 0.5 and 0.5 and 3.5. We can adjust this. So, if my window is bigger for my y's, I have a bigger window for my x's. If I make my y window get smaller, will this range of x's work? No. So I would have to make that window of x's get smaller. So I would have to go all the way down to here so that I'm only getting points that fall in that blue area. Does that make sense? So if I make my epsilon, my 3, I want to be even more accurate. So I have a smaller window. What's going to happen to my window of x's? It's got to get smaller. Okay, so then all of a sudden now I'm in the good range. So I have found if I pick x's in between these two numbers, my y will fall in between these two numbers. So that's what epsilon delta, the actual definition, means. You can get as close to the true value of the limit as you want by making your x's get closer to the number we're approaching. And that should be true. If it's truly a limit, haven't we seen as we make those tables? If I only put in, if I'm approaching 2, if I put in 1 and 1.5 and 1.75, I may not see yet. But if I put in 1.9, 1.99, 1.999, isn't my limit getting closer to the true value? Yes. Okay. So, I don't know if I really want to do this on a graph though. Let's try it. Let's do our graphing calculators for a second, just because I know I told you wouldn't need one. We're not really going to use this ever in terms of it, but it's just for understanding purposes right now.
So how do we get an epsilon?
You can.
Oh.
Okay. So on this, I want to find, if you have scatter plots turned on your graph, you need to probably turn those off. Okay, so if I'm going to go to my y equals here, I want to use a graph to find a number delta so that the distance between x and 1 is less. If the distance between x and 1 is smaller than delta, then the distance between this function and 2 is less than 0.02. All right, so this is like a limit. If I'm talking about the distance between these, we subtract them. So if I want to really think about my function, okay, if this absolute value is less than 2/10, that means the actual value has to fall between negative 0.2 and positive 0.2. Would you agree with that? Absolute value, compound inequalities. So let's say it's an and. So the true distance is between negative 0.2 and positive 0.2. If I add my 2, then we get negative 0.2 plus 2, 1.8. So we actually need to know when the y values of this function fall between a positive 1.8 and a positive 2.2. So here's what I'm going to do on my graph to illustrate it. I'm going to graph all three of these. So I'm going to graph 1.8, my function, and my 2.2. I'll throw in my function first. X cubed minus 5x plus 6. And then my y2, I'm going to set it at 1.8. My y3, I'm going to set it at 2.2.
Doesn't matter what order it's in.
Okay, now I can't see a lot here in my standard viewing window, so we might need to zoom in a little bit. So you can either use the zoom in feature or you can adjust your window. So I'm probably just going to go to my window.
Wait, did you put the -2 in on your...
No, because we already added that to the ends. All right, so let's just look. It was all positive, so let's look between, I'm going to set my x's between 0 and 5. Okay, so I set my window, I did my x's between 0 and 5 and my y's between 0 and 5 so I could kind of see this. So I'm looking at my function. I am finding the distance between x and, what was it? 1. So 1 is the number we are approaching here.
That was your 1.8.
We graphed that. I set my window to be between 0 and 5 for both my x's and my y's. So we are approaching x equals 1. Right? That's the number we care about. We need to find what would be acceptable. Okay, so can we agree that this is about the point when x is 1? So anything in this little window would be an acceptable value. So we just need to find these points where they meet. So remember, you can do second, trace, intersect. First curve, it tells you up at the top which one it's looking at, so it's looking at my cube function. Second curve, I'm going to go to my top line here,
What did you put in your first curve?
my function, my x cubed function, and I'm doing my second one to be that top line. And then you have to do your guess, you have to tell it which point we're looking at. So we're looking over here. And if you're having trouble doing this on your calculator, it's not a big deal. I'm not going to ask you to do it. I'm just using this to illustrate. So we get 0.911 as our value. Okay, so that means x has to be and so if I want the second one, so we go second, trace, intersect. First curve, I want my x cubed again. Now I want the bottom line. Enter, and 1.12. Now obviously I do have a little rounding error here, but what I just illustrated from this graph is if I want to be within 0.2 of the true limit, I have to pick an x value between 0.911 and 1.12. If I plug in any number in there, I should be less than 0.2 away from the true answer. Okay, so we're just kind of right now trying to understand what this is talking about. delta is how close you have to be to x. Epsilon is how close we have to be to y. So we're saying if this is a true limit, I can get closer to my y just by getting closer to the true x value. That's what this is all saying. Any questions so far? It takes a while.
So it's
Be
okay,
patient.
it's okay for just a little bit.
Yes.
Like I don't, like I.
Well, you should have some idea. Like, you understand what a limit is, that we're approaching a number.
I don't know.
Do you understand that if we get closer to x, we get closer to the true limit value?
No.
Well, we should know that from our tables anyway. If you want
I
to get,
got really confused when we had the Desmos open with the two different colored lines, but then when the one was getting smaller, the other one had to get smaller.
yeah, if you want your answer. So if you're making a table of values, okay, and I'm trying to estimate a limit, and I'm trying to find the limit as x approaches 3, okay, and you're trying to guess it from a table. Are you going to get there if you just plug in 2 and 2.1 and 2.2? No, what do you have to do to get closer to the true?
2 lines.
Yep, you have to get closer to 3. So to get closer to the true limit, we have to get closer to our x value. That's what this is saying. So the actual definition says, if this is the true limit, I can come up with a rule for how close. So that if you say I want to be within 100, I can just automatically say, okay, pick x's between this value. And if you say, nope, 100th isn't enough, I want to be within 1,000, I should be able to say, okay, pick x's in this window. So we have to come up with this rule of how close x needs to be to give us the accuracy level we want.
So we're just kind of going in reverse as if they tell us how close we have to get.
Yeah.
Okay.
So what we are actually doing with this, other than trying to grasp what it's talking about, we are going to do what's called a proof, essentially. It's like the epsilon delta definition. Skip that one. So if we want to use this epsilon delta definition, there are really 2 steps. This is the slide that you want to highlight, box in. This is what we are going to do every single problem. Okay, I am not trying to complicate this more than it is. There is no trick to this stuff. Every problem is going to be the same. And you will see the pattern, but it's going to take us a few examples to get there. So I'm just asking you to be patient. So we are going to start out with a proof. You have to use very precise definition. So we are going to state, given an epsilon greater than 0, okay, we will first use the f of x minus L is less than epsilon, so the distance between our function and our limit is within this window, to find a delta. Then we are going to prove this works by showing the definition. Now I already told you the 0 is less than is kind of redundant, so we can drop that. This is the actual definition. So we are going to be using this sentence over and over again, just by subbing in some different values here. So when we do these, we're going to work through a couple today. I'm going to be very particular and precise about my language and how I set them up, and everyone's the same. It's a proof, so it's if another calc student walked in and picked up your homework, they can read it and say, okay, yep, that justification makes sense. I can't disagree with this. This is true. So if I want to prove the value of the limit as x approaches 3 of 4x minus 5 is equal to 7. Okay, first of all, is this limit equal to 7? Yeah, by our limit laws. Now we're trying to prove it using the epsilon delta definition. So what I recommend first, I always write my goal. This is what I am trying to do. And this is the line I am going to reference over and over again. And that comes back to this definition. So if the distance between x And what value of x are we approaching? 3 is less than delta. Then the distance between my function. What is my function? That's the limit.
4x minus 5.
So the distance between the 4x minus 5 minus the limit, which is 7, is less than epsilon. Okay, so I plugged in my a, which is the number x is approaching, my f of x, which is my function, and my L, what the limit is equal to. That's what I have to prove.
Wait, what did you say A was?
The number we're approaching. So step 1 is kind of just like our work. We are going to find delta. So we're finding a formula for delta. Alright, to do this, we are going to work backwards. So we are going to start with this statement. Actually, I won't put the less than epsilon yet. That might make it a little more obvious later on. Okay, so let's start with that. Just the absolute value. If I wanted to simplify this, what could we do on the inside? Okay. So would we agree that's the same as the absolute value of 4x minus 4? What could you do now? And since 4 is already positive, it would be a positive number. Come out. Yes. Okay. Not less than delta. Well, yes, you're a step ahead of me.
Oh.
Okay, so we're starting with this statement, right? This thing is less than epsilon, right? So can we say at the end this would be less than epsilon? If you don't like how I set this up, I can work down and treat it more like an equation the whole way down. So if I lose you, I can set it up differently. Okay. Notice, we've seen the absolute value of x minus 3 before, haven't we? How would I get that by itself?
Multiplied over 2, divide by 4.
Divide by 4. So what I'm going to do, delta is going to be epsilon over 4.
Wait.
Okay, if I took this right here, we said divide by 4, so x minus 3 is less than epsilon over 4.
And then that is delta.
And we said up here, x minus 3 is less than delta. So all I'm saying is, I'm working this out, started with this inequality, okay, I worked backwards until I got that in the absolute value. So this over here is going to be my delta.
Okay.
Alright, so that's like our scratch work.
Okay.
Scratch work.
Now we do the actual mathematical proof.
Oh.
So the proof is where we have to be pretty precise in our language. We have to start the same way every time. So I'm going to say let delta equal epsilon over 4. So first you have to tell me what delta is. Then, and now we're going to kind of, it's going to feel like cheating, but we're going back to our goal. And we're going to basically restate that goal. So then, if the absolute value of x minus 3, maybe we shouldn't say then here, that's too many thens. If the absolute value of x minus 3 is less than delta, then the absolute value Now I'm going to stop for a second. My proof is if I can say this full statement. Okay, I currently have said this much. So now I have to mathematically show that this is less than epsilon. Okay, we're really just going to repeat what we did in our work phase. So, this is the exit value of 4x minus 12. And that's 4 times the exit value of x minus 3. Okay, so everybody with me so far? Okay. But, if the absolute value of x minus 3 is less than delta, then this has to be less than 4 delta. Okay, because I went back and I used this. I have an absolute value of x minus 3, and I know that that thing is smaller than delta. So 4 times that would have to be smaller than 4 times delta. Okay, that's good. Look back at our goal. We just got, oh, I want to scroll. Yeah, that's annoying.
I don't know why.
Won't scroll.
Don't you need to be on your thingy and not your
It shouldn't matter, but we just got the less than. What's the last thing I need to complete my proof? We need the epsilon. So let's come back. Is there any way we can get this epsilon in here? What is delta equal to? And 4 times epsilon over 4 is epsilon. So I have, if the absolute value of x minus 3 is less than delta, then this is less than.
Wait. Okay. Where did we do our delta equals epsilon over 4 again?
We did our scratch work and basically found a formula. So that tells me, if I want my y to be within 1 of my true limit, you have to pick an x within 1/4 of the x value we are approaching. If I want my y to be within a half, your x has to fall within 1/8. So x has to be a 1/4 of whatever you want your y window to be.
So which one's correlating to x and which one's correlating to y?
Delta goes with the x, epsilon goes with the y.
So how
So
can we,
why, no, you go first.
so for step 2 for the proof, how can we just say that delta, that's delta?
That's what we were trying to do, is essentially find a formula. So that if you tell me how accurate your y needs to be, I can tell you how accurate your x has to be. Think of it in real world terms, okay? If you're manufacturing parts, does every part come out of your machine the same? No. But you know what range of sizes will fit what you're trying to make the part for, right? And so this is telling me, how do I have to calibrate my machine to make that happen? So you tell me what's acceptable. My calibration says, okay, I'm going to take that number and divide it by 4. That's how I have to calibrate my machine to guarantee that the y it spits out falls within an acceptable range for you.
Okay. Sure. Okay.
So I
Wait. Oh, I'm locked, I'm ready for.
Yeah, you should not be able to do it by yourself.
Why
If
is there a
you
hand
could
up
do
then?
this by yourself now, I'd be super
Why is
impressed.
there a hand up then?
Quit complaining.
I'm complaining.
We're looking at an example. Let's go.
Well,
So-
I'm just scared.
I want to prove that the limit as x approaches 3 of 13x minus 29 is equal to 10. Okay, we are going to do these. It's the same process every time. The first thing is to write our goal, which is the definition. Definition is if the distance between x and the number x is approaching, so that is 3, is less than delta, then the absolute value of f of x
13x minus 29.
minus the limit is less than epsilon. That's what we have to show.
Why would you use the tracking pen?
What?
Oh, never
So the first step is like our scratch work. We have to find out a formula for delta. What will be acceptable? How do I have to calibrate my machine so it spits out parts that will work? So we're going to start with the end. So when I take this, the 13x minus 29 minus 10, what can you do in there?
Take out 13 and you get 13x minus 3.
Yeah, it's 13x minus 39. Take out your 13. But we know that this inequality is less than epsilon. Okay, if it confuses you when I write it this way, you're welcome to think of it like this. If you want to write the entire inequality and work down. If that makes more sense to you, you can. So how would I get this absolute value of x minus 3 by itself?
Divide by 13.
So this time we're going to do epsilon over 13. So if you tell me within 1 is acceptable, I'm going to say, well, x has to be within 1/13 of that. So when you get here, that's what we are going to use for delta. So when we do our proof, the first thing we're going to do is write delta. So I'm going to say, let delta equal epsilon over 13. All right, is everyone with me? Now we have to prove it. So we're going to go back to that goal statement, and we are going to restate everything up until the less than. So I'm going to say, if the absolute value of x minus 3 is less than delta, then the absolute value of 13x minus 29 minus 10. And now I have to work it out until I get a less than and an epsilon in my problem. Okay, but it's really the same thing as that we already did when we were doing our scratch work. So this is 13x minus 39. Then we take out the 13. Okay, but we've already said that the absolute value of x minus 3 is less than delta. So 13 times the absolute value of x minus 3 is
1.
less than
13 delta.
13 delta. So I just got my less than. All that I need left is to get an epsilon. Okay, so this equals 13 times epsilon over 13, which is epsilon.
Wait, I was doing good until we got the delta.
Okay,
Where did we get the delta from?
from this statement right here. So once I saw this,
Oh,
I know that is less than delta. So 13 times that would be less than 13 times delta.
So that's equal to.
you said that we shouldn't be able to do it by ourselves, and I really wanted to do it by myself. So
Challenge
I
accepted.
was doing it by myself, and
That's impressive.
I was not listening until we got to the end, because then there were too many things happening.
Okay, so something delta is.
I'm proud of you.
So when we end up with the epsilon, what exactly did we prove? Like what
We
do our
essentially
numbers mean at that
Found
point?
a formula so that if the manufacturer comes and says, I need a part to be within 100 of this measurement, you can say, okay, I have to calibrate my x to be 100th over 13. Like, you know how to find your x value that will work. So no matter what window they give you for y, you can instantly say, okay, this is
So
what it
we're
has to
making
be.
our own equation to plug x back into.
So this is like the true definition of a limit as a proof. We are going to do a couple more of these, probably 3, 4, however many we need together tomorrow. So we'll do more until we feel confident. We're probably not confident yet. I said handout because it's available if somebody really feels good after this. There's a handout on Classroom, but I would not recommend starting that yet unless you just really feel like you can.
Oh, I'm lost.
So tomorrow, we're just going to do more of these until you guys can tell me what the next step is, and then I'm gonna turn you loose to do them on your own, okay? Every step is the same, like, they're very identical. So once we do enough, you will catch on and it'll be okay. We've only done 2 together, so I don't expect you to be there yet.
Why is it always absent?
Because that's distance, it could be, distance has to be positive. So if I'm measuring the distance between something and 3, it could be a number smaller than 3 or bigger than 3.
Yeah.
So we always subtract because that's how we.
Yep, you find the distance by subtracting.
Okay.
How are you